Okay, welcome back to CE 529. We are talking about how do we use micro simulation in traffic safety, in the area of traffic safety. And this is becoming more and more critical, and we'll have a guest speaker next week who will be able to elaborate a little bit more on it, and not necessarily about simulation per se, but the ideas that we use to estimate safety using micro simulation. Those ideas are very similar to what happens when we are, yeah, so there are folks saying online, I'm here too. Okay. It looks like they can hear, so that's good. Yeah, thank you for letting us know, Simon. So we are, so you'll see that the ideas that we use to estimate safety from simulation, they are becoming more and more prevalent, even in the real world with the video analytics that's now becoming more and more available. So some of that experience actually translates really well into using, or some of those metrics that we use, they translate really well into real world when we get into video analytics. And then there are some applications that flow from that. So we'll talk about all of that in here. So we'll try to wrap that up today. And then I have a couple more items that I need to cover on modeling and two fluid models and stuff like that. So yeah, we're getting close with this course as well. So first of all, what is the purpose of using, what is the traditional approach to safety analysis? And is there any benefit to doing that via simulation, right? So safety analysis, one of the difficulties is that, safety is completely dependent. How we estimate safety, it's completely, almost wholly dependent on collision statistics or crash statistics. So we look at historical data. In fact, if you look at highway safety manual, they will tell you, if you want to figure out whether a location is safe or unsafe, you will know it in 3 years. If you look at 3 years worth of collision data, you can analyze that data, and then you can use that data to figure out how many crashes are expected on this location. And then you can compare it to all the other similar locations and figure out if any location is having sort of more unusual collision. So I hope you can see the problem with this, right? Like, it requires 3 years worth of data to figure out whether something is safe or not. So what that means essentially in practice, that you're going to for 3 years, you're going to let all those collisions happen before you can even do anything about it. And that's a big issue. And I mean, the problem is that we have so many locations with so many crashes that, yes, we cannot fix everywhere. But philosophically, it's a big issue if you cannot even make an assessment of something being unsafe until you have 3 years of injuries and deaths having to occur at that same location. So that's the big problem. So we don't like that. So we can probably, if we can come up with what we call some surrogate measures, which are not collisions by themselves, but some other measures that get us to that point where we can make estimate about the collision. Okay. So that we can do that analysis more proactively rather than reacting to situations 3 years down the line. We can hopefully make that assessment sooner. And then the next question is, other problem is, like, let's say if you come up with like a more innovative design and innovative road design, and you don't know whether it's safe or unsafe, then how do you make sure it is safe? So one thing that's where also simulation might be able to help you, that you simulate that design in a computer model like we've been doing with vSim, and then estimate those surrogate measures other than collisions that we have. Okay? So these are the two reasons why this surrogate safety-based analysis that you can do using simulation could be valuable. You can be more proactive in assessing safety problems, and you can more appropriately assess the safety of newer designs that you might have come up with. Okay, so surrogate safety assessment model, it's a Federal Highway Administration developed this model. And it's a combination of microscopic simulation and automated conflict analysis. which is able to study the frequency and character of narrowly averted collisions. Okay, so narrowly averted collisions would be near misses. And here it says vehicle to vehicle, but it doesn't necessarily have to be vehicle to vehicle. You can do automobile to automobile, you can do automobile to pedestrians. You can figure out how close two agents or two users got on your node network. Okay? And then if they're getting too close to each other, that might be an indication that a collision might occur as well. SM provides a great opportunity to get the safety of roadways, of traffic facilities without waiting a long period to observe the crashes and injury after the construction of any facilities, roads, roundabout, intersections, whatever. Okay. So what we are going to do is, instead of analyzing, because obviously in simulation setting, we are not going to observe the crashes, but we'll observe how close these two vehicles got to each other. And if that distribution of how close they got to each other moves to be time and space distance between those two agents, they get very, very close, then you can expect that more collisions would also happen on that road, because the design is such that the drivers are having to, or drivers or other road users are having to make those types of maneuvers. Okay. So SM analyzes the frequency and character of vehicle-to-vehicle conflicts. So SM is the surrogate safety assessment model. It's a computer program that you can download on your computer. It's free. And for this purpose, SM uses the trajectory files of traffic simulation packages to recognize the type and number of near misses. Now, this is where your simulation is so useful. You have what we call .trj files. So these files are called, so if you take your vsim model, from your vsim models, you can always export what we call .trj files. These TRJ files are trajectory files, and they document every 10th of a second or whatever resolution you have specified. Every 10th of a second, it will record where each individual vehicle was. Okay. And then what surrogate safety analysis model does is it takes that trajectory file, and then it tells you how many times vehicle got closer than a particular threshold. Okay. How many times vehicle got, and there are measures that we're going to talk about right there at the bottom of this. For this purpose, SM uses trajectory files to recognize the type and number. And then here are some key here's the key measure of effectiveness or measure of performance, which is time to collision, TTC. Okay. So you specify TTC threshold to be 1.5 seconds, and SM will tell you how many of the vehicles in your overall model got closer than that 1.5 seconds. And you can change that threshold also in SM. So you could say, maybe you're interested in conflicts that got even closer than that. Maybe if they got TTC less than 1.2, then it will only count the vehicle conflicts at 1.2 seconds, and so on and so forth. Yeah. So here is the key thing though, like, you can, this is not just applicable to simulation anymore. Nowadays, there are programs that can do that type of analysis for you even in the real world. And how do they do it? We video record a certain location on the roadway, and then we apply video analytics to that. And that's what our guest speaker is going to talk about next week, is that how can you take the video analytics from a real world situation, convert that into trajectories of vehicles, and then apply same types of threshold. How many vehicles got closer than 1.5 seconds? Okay, or 1 second, or whatever your threshold is. How many near misses actually happen? So you can estimate that. So what we call that technique is the traffic conflict technique. Okay, traffic conflicts are a technique to assess the safety of a location with understanding that conflict frequency is correlated with the risk of actual collisions. Okay, so if you have more conflicts happening, more collisions will happen. And this is sort of a very simple idea that you see it all the time when you're talking about let's say a 4-legged intersection versus a roundabout. So you can see what's happening is that all these points are conflict point at a location. So if you have, so vehicles are moving both directions on these east-west and north-south road, okay? So there are, you can see that there are 16 different crossing conflicts that might occur. Okay, this is basically, if you look at these conflicts, this is if vehicle is turning left from here, and then this vehicle is turning left at the same time, they will have this conflict point right here. Okay, if vehicle is turning left, and then this vehicle is going through, there is another conflict point right here. So if you count all these conflict points, you have a total of 16 crossing conflicts, 8 merging conflicts, and 8 diverging conflicts. And then, merging and diverging conflicts are okay, usually not the biggest of the big deal, because, diverging conflict, we don't worry about it as much, because they don't tend to, generally speaking, they don't tend to, like, sometimes they could cause some rear end type conflicts, or rear end type collisions, but they're not going to be as severe. And merging conflicts could also be somewhat severe, when you have a vehicle going through from here, a vehicle turning right. So, there might be some collision chances over here. But the most severe type of conflicts are the crossing conflicts, right? Because you can see if a collision happens between a vehicle going this way and this way, it's going to be like a T-bone type collision, which is almost certainly likely to be more severe than any other type of crash that you might see. Okay, other than head-on possibly, but obviously we have mostly divided roads, so we have fewer chances of head-on collisions that we avoid. So head-on could be most severe, but other than head-on, these crossing conflicts type are the most severe ones. Yes.
What are diverging conflicts?
So diverging conflicts are simply where you have somebody trying to turn right, okay, and then somebody's going through on this road, and then those diverging conflicts might occur if your right turner just suddenly slows down. Okay, and then your through guy, through person is like, they're still thinking, okay, I just have to go through, so I'm just going to keep going. So there might be some conflict point here, but typically, again, these even if they lead to collisions, they're rear end collisions, so less severe. Now, and this is it's an unrelated point to this, but when you're trying to estimate, think about like if somebody asks you why are roundabouts typically safer than signalized intersection or any four-legged intersection, this is your answer right here. Because in a roundabout, you basically eliminate these crossing conflicts. All the conflicts that you'll have now in a roundabout are going to be merging type conflicts. Okay, they're all going to be merging conflicts rather than crossing conflicts. So that's why. So this is sort of something that you could come up with. Like if you sort of eliminate all these crossing conflicts, then the situation generally becomes safer. And then you can use conflict techniques to figure out, what type of, and then obviously number of conflicts also depend on the total volume that you have, right? If you have, you could have a four-legged intersection, but if there is nobody actually coming in through the street or very low volume is coming, then you obviously your crossing conflicts will be down as well. So this is sort of, a diverging diamond intersection design. A diverging diamond intersection is a more complicated design, but what I wanted to show you here is that, like if you have in diverging diamond and all these types of sort of things, we also again try to eliminate what we call the crossing conflicts. Okay, so instead of having, and you could look up, what the details of the diverging diamond design is, but let's say if you have this major highway going east-west here, okay, and then these minor roads are coming in from north and south, what you can do is you can sometimes eliminate a lot of the crossing conflicts by eliminating the direct left turn, onto the major road. Okay, so what we are doing here is that, let's say if this is a street, you want to go left, we are not actually going to allow you to make a left turn. Okay, we're going to pause the left turn. We're going to make everybody go right. And if they need to, if they need to, do something, we will provide like a U-turn at the back end on either side. And then you can make those. So basically the idea of all these innovative design, like diverging diamond interchange and super DDI and all of these is to sort of eliminate some of the crossing conflicts by taking away certain left turns. And so again, like, this shows you the red ones are the crossing conflicts. So you could see that, sometimes you can take away some of these cross, and then it doesn't mean that, you always have everything completely taken away. So in this diverging diamond interchange, what happens is that you almost have somebody going the opposite direction. So in this one, what we are doing is that we are having folks to go this way, and then they come back this way. And then, so this stream, and again, there are some traffic volumes here that will govern how many conflicts you will have. But again, the key thing to observe here is that you always want to make sure that you're trying to minimize these crossing conflicts. In some conditions like this, you could see that, this DDI design might be a safer design because it only has like two crossing conflicts, right? It only has two crossing conflicts here. But if the volume that's going to take those crossing conflicts is too high, like for example, if you just look at how many crossing conflicts you have, you'll see there are only 2 here, but then there are 6 over here in this design. Okay. And again, I'm not even going to go into the specifics of the design necessarily because that's not the point. But what I'm trying to show you is different movements. And on these different movements, you're seeing 6 different crossing conflict types here. And then on a DDI, you are only seeing 2 of these. Okay. But if you look at the actual number of traffic volume, if you look at the total number of traffic volume, even though there are 6 of them, you're going to actually end up with, you could end potentially, depending upon what the volume shakes out, you could end up with like having total fewer conflicts on where there are 6 different types of conflicts or crossing conflicts. But here there are only 2, but there is so much volume using those 2 conflict points that you might end up with less safe situation with a DDI rather than a DDI. So what I was trying to say is that, yes, roundabouts do eliminate conflicts, so they are safer like this, because now we have eliminated these 16 crossing conflicts, which is great. But sometimes this picture could be misleading, not in the case of roundabout. Roundabouts certainly are safer. But in a situation like this, where you say, I only see 2 crossing conflicts here and I see 6 here, but that doesn't mean that super DDI is always going to be unsafe, because that will depend upon how many vehicles actually are ending up making those conflicting turns and stuff like that. So always look out for that. So volume and distribution are also very interesting to note when you talk about conflicts. So I want to go back to the SSAM. So SSAM was Getman and Head 2003. It was the first attempt to develop a surrogate safety measure-based approach. And then all of that work resulted in the development of SSAM in 2008. So it's a long time ago now. And then they've come out with, like, I think this is the 3rd version of SSAM now. And then, we wanted to see to what extent the analysis that you do in surrogate safety assessment model, how does that translate to the actual safety? So when you talk about validation and calibration in this context, you know what that is? Validation and context in that sense is you do the conflict analysis using SSAM, and then you look at historical data from that same location. Okay, and see if those things correlate or not. Okay, so maybe what you do is, maybe you look at, so there are studies that have been done. They simulated 20 different signalized intersections. Okay, and they simulated, and then they looked at the collision data, 3 years worth of collision data for those intersections. And then using the simulated models, they estimated all the conflicts. And then they analyzed if the conflicts correlated with the actual collisions on those locations. Okay, and they, for the most part, they did see that there is a significant correlation between what happens in the simulated conflicts and how many crashes you were observing, which is great, right? Because now, if you know that high collision locations are also your high conflict location when you analyze it with simulation, that means you don't have to wait 3 years to figure out which locations are most dangerous. You can actually build a reliable simulation model, and based on that, do your safety assessment. Okay, so that makes simulation a very powerful tool here even for safety analysis. But the calibration of the simulation model is very critical. So if you take a well-calibrated model versus like a maybe, so there would have been studies that looked at well-calibrated model versus sort of like, that used all the default parameters. They saw that they could improve the correlation between collisions and the simulation by as much as 50%. They could improve that. Okay, so what this study found was that if you do well with your delay model and your travel time model through an intersection, so if you can correlate delay and travel time, so that means you're capturing the stoppings, the acceleration after the stopping and all of that correctly. If you're able to capture all of that, then your safety outcomes are also very accurate. Okay, so this is also good news, right? Because now, if we build a good model that is very well calibrated for travel time and merging and all of that, that means that we are also building a very accurate model for safety, which is great, right? Which is something, again, it's very useful for us to be able to do that, because again, we are not using 3 years worth of collision data. We're able to do it using a simulation model. So this tells me that I don't have to do like anything super fancy to build surrogate safety assessment model. If I'm building my simulation model right, where my merging behaviors are accurate, my stoppages are accurate, my car following is accurate, then my travel time and delay would be good too. And then if I use that model for safety assessment, that will work just as well too. So there was like one study that found that if you estimate the collision conflicts at an intersection, okay, if you estimate like annual number of conflicts, and if you do this 0.119 times conflict raised to power 1.419, this number, actually this equation works really well, at least for signalized intersection. For signalized intersection, you can estimate the number of crashes one would expect using this little formula. And again, the specifics of this formula I don't care about, but what is important is that, yes, as the conflicts go up, crashes go up as well, and they go up with some sort of exponent power, and then there is like a calibration factor at the beginning, 0.119. Okay, so, and there is a paper about that, and I provide a link to that if you want to look through that. But the key message here is that yes, crashes do indeed increase as the conflict increases. So you can make a pretty good safety assessment just by looking at how many conflicts are happening at your simulation model, and use that to then say, okay, I can forecast my crashes, or at least get a good sense of. And especially you can make very good relative assessments very nicely. So if you have two different intersections, you can look at the conflicts. Whichever one has more conflicts, you can expect them to have more collisions as well. Yes.
The state conflicts like the 30 number or
no. So this is so these 32 are like sort of, so these are, I'm calling them conflicts, but I should, if you want to be more accurate about it, I would call them conflict locations. Okay, so these are points of conflicts. Okay, so what I'm calling conflict here in this equation, they are a little bit more interesting than that. It's the actual number of times the vehicles got close to each other. And how do I define close? I define close based on a threshold that I'm going to provide to the model. Okay, so I'm coming to that right this second. Okay, so based on previous studies, the 1.5 seconds TTC, which is time to collision, SM default was found to be the most recommended threshold. Okay, so if you look at, so this is a simulation model, and SM does that for you. Take the model, and then it tells you. So if you look at all these yellow signs, this is where the time to collision was less than 1.5 seconds. So that means vehicles got as close as 1.5 seconds of each other of getting into a collision. So they came within 1.5 seconds of getting into a collision. Okay. Now, if you look at these red places are locations where vehicles got within 1 second of colliding with each other. Okay, within 1 second of colliding. So the difference between the time that one vehicle passed that point and another vehicle passed that point was less than 1 second. So those are your red points right here. Okay. And these yellow points are 1.5 seconds. So obviously you can see, and green points are less than half a second. So you can see the green points are where the collision, like the vehicles got within half a second of each other. These are the locations where vehicles became or so close that they were only half a second away from having a collision. Okay, so you can see obviously the green conflicts are more severe, and you can probably tell what is TTC equal to 0 second mean? Time to collision equal to 0 second. What does that mean? A collision has happened, right? And you won't see that in the simulation, but and then 1.5 second is the threshold that's already specified in the surrogate safety assessment model. But you can play around with that, like if you're looking at that. So there was a study, the same study that I talked about just now. This study, they said if you make your time to collision 1.6 seconds, that improved the accuracy of the rear end conflicts. So that means that if you specify 1.6 seconds to be the threshold, then that sort of defined, that correlated better with the collision experience of that location. So you can play around with this threshold too, but they didn't see any other, for other types of conflicts, they didn't see any benefit of increasing that threshold. Okay, so you can specify different threshold. And then once you have the threshold, you can also categorize the conflicts. Okay, you can categorize the conflicts into three things. And that's based on the approach angle that the two users had. Okay, so you could have an angle. So if you look at this approach between this vehicle, it's going this way, and then this vehicle is going this way, you can define that based on theta. So if the theta is 0 degrees, what happens? That means what type of conflict do you have? If this angle is 0 degree, what will happen? I would have moved. That means this vehicle will basically be over here, right? And if the theta is 0 degrees, that means this vehicle is not approaching from this direction. This vehicle is also approaching from this direction, right? If the theta is 0 degrees. If this is equal to 0, then your approach angle for this vehicle won't be this arrow. It will be denoted by the new arrow that I have. So then what type of conflict would that be? Rear end type conflict, right? It will be a rear end type conflict. And then we take like, okay, anytime within like between 0 and 30 degrees, okay, between 0 and 30 degrees, we call it a rear end conflict. That we say like, okay, they are essentially moving in the same direction if the approach angle is less than 30 degrees. Now, if the approach angle of two vehicles is between 30 and 85 degrees, okay, between 30 and 85 degrees, then we say, okay, that might have been like, that might have been a lane change conflict. Okay, because these types of conflicts happen when vehicles, so 30 to 85 will make your vehicle either like, something over like this, right? So there will be like, and maybe even like a little bit. So 30 to 85 degree, if the initial approach direction is 30 to 85 degrees, we call it lane change conflict. And then anything above 85, we call that a crossing conflict. That means, you have a higher risk of colliding in a T-bone type fashion if your angle exceeds 80 degrees. Okay. So when you analyze any trajectory file with SM, it also tells you what type of conflict it was, because it's also looking at where those vehicles were approaching from when they avoided that collision. Okay, building precise simulation network is one of the most important steps to get the useful SM results. So yeah, what you've been learning should help you build good, safety and assessment model as well. Some conflicts might be observed with TCC being 0. Obviously, TCC 0 means crash, but that could happen because if your links and connectors are not well drawn. So, and if there are overlapped links in the model, so yeah, you want to avoid that as much as possible. That's what we've been talking about in the lab as well, right? We don't want to have very significant overlap between two links, and like you might have some, but you try to minimize that as much as possible so that you don't observe that TTC equal to 0 situation. Okay, and then critical behavior parameter to get valid results. We've seen this chart before. So adjusting car following, gap acceptance, lane changing things can help you not just with your calibrating very well your simulation model, but then also doing the right thing from a safety assessment perspective too. So we've seen that. So surrogate measures that we use. So time to collision is the most important one. We use it all the time. And then there are other ones. Minimum time to collision, minimum post-encroachment time, PET, initial deceleration rate, maximum speed, maximum relative speed difference, and all of those things. Okay, so these things, and then the location of the event. Not exactly a surrogate measure, but it can tell you which location is more dangerous than others. So if you look at the chart that I showed you earlier. So in this chart, you can say that this is a location where vehicles are getting too close to each other, right here. Okay? So this is the location. This is a location potentially the vehicles are getting too close because I see some reds there. Okay, or some of these greens could be even more conflicting locations. So, okay. So let's talk about this real quick. So what is happening in this location? It's a time-space diagram. Okay, it's a time-space diagram. And this time-space diagram, you have two vehicles. One is the through vehicle. So I'm going to try to highlight that. So this is the trajectory of the first through vehicle right here. Okay. And then this is the trajectory of the crossing vehicle. Okay. So these are the two vehicles that I'm interested in to define all these different parameters, these conflict points that I talked about. So when we say time to collision is basically the projected arrival of the two vehicles on the conflict points. Okay, so if through vehicles continued in its path without any acceleration or deceleration and maintain that same speed, they would end up here. Okay, and then the crossing vehicle, as it arrives, it's going to end up here. And then because distance x being the same at this point, so it's a time-space diagram. Time is on the x-axis, distance is on the y-axis. This whole line represents the same point in space. This represents the same point in space. And if the through vehicle continued on its trajectory, this would end up on that space. This is the time T4 during which this through vehicle will end up at that same location. And then there is a crossing vehicle that's trying to cross that street and it's coming from somewhere else. And that would reach here at this point. So time to collision is basically if through vehicle didn't do anything and crossing vehicle didn't do anything, they took this path, what's going to be the time difference between their arrival at the same conflict point? Okay, so that's your TTC, time to collision. And that's based on the projected arrival at conflict point. Now, if this through vehicle actually is able to adjust something and maybe decelerate somewhat, okay, so this initial deceleration rate could be also a surrogate measure of safety. Because if the vehicles that are going through are having to decelerate too many times, that means they're having to avoid that collision a lot of time. And it's only a matter of time when somebody maybe looking at their cell phone or whatever reason might not be able to do that, might not be able to generate that initial deceleration rate that is required for them to change the path. Okay, so that's another one of these surrogate measures. If this deceleration rate required increases, that could be a problem for some drivers who might not be able to generate that deceleration rate for whatever reason, because of distraction, some issue with the car, whatever it is. So, and then because of that deceleration, then the vehicle ended up here. And then if you compare that to the crossing vehicle's arrival, that becomes the projected arrival at, this is the actual arrival at conflict point. And then we call that what we call the PET, the post-encroachment time. So that's how much, so basically that's only the time difference between the actual arrival of the crossing vehicle and the through vehicle on the conflict point. Okay, so that's your PET. Okay, and then let's see. So yeah, and then I want to talk about maximum speed and maximum relative speed difference. Maximum relative speed difference is basically just kind of looking at what is the relative speed difference at which they are approaching that conflict point. Okay, and then maximum speed is the maximum speed of the crossing vehicle. So crossing vehicle, you could see basically I'm just figuring out at what point this slope is the maximum. What's the fastest that the crossing vehicle is ever driving? Okay, so that's so those are the few, but the most widely used conflict measures are PET, TTC, and the initial deceleration rate, because they have been found to be most related with collision experience, and TTC being sort of the most important time to collision. Okay, so this is sort of the SSAM's filter. So basically, this is a TRJ file that you will get from your vSIM output, and you will add that to the mix, and then you specify some time to collision thresholds. So basically, this is telling SSAM that only count the conflicts where time to collision is less than 1.5 seconds. If you change this number, then that will become your threshold. And then maximum post-encroachment time, 5 seconds. Again, you're specifying if anytime this time less than 5 seconds, then tell me that that was a conflict as well. And then it also wants you to have, and you can specify both of these, and then conflict angle threshold. This is the two angles that I talked about, 30 degrees and 80 degrees. So these are these thresholds, 30 degrees instead of 85, they're using 80 in that figure. But again, you can play around with that, usually 80 degrees. And these are, I believe these are the SM default, okay? And then you analyze the file. And then once you analyze the file, it can, it provides this type of an output to you, okay? It tells you what is the average time to conflicts, average post-encroachment time, all of that. And then how many of them exceeded 5 seconds or how many of them exceeded 1.5 seconds, and so on and so forth. So what I'll do is that once you're done with this model that you're building with the roundabout, we'll do a quick lab on actually taking the trajectory files from these roundabout that you just modeled, and then be able to get the conflict data out from the SM. Okay, so that'll be one project that we're going to work on, and so we'll go from there. And then yeah, so that's basically the idea of SSAM, and then you can export all the results to a CSV file. You can do some post processing, but we'll talk about that in the lab context. So yeah, this is basically what it is. What I have here for your surrogate safety based assessment. Are there any questions about this? Any questions? So I think this is the key thing, right? When you work on the lab, you'll probably come up with some questions. So we'll talk about those in that context. But the idea would be to take the trajectory file from vSIM and input that into surrogate safety assessment model. And then, by the way, so what our guest speaker next week is going to talk about is basically doing the same thing, but now with the video analytics data. So try to derive these time to collision, post-encroachment time, all of that, by automatically analyzing the video data. So how close two vehicles got, how many near misses were there, and we know that they correlate with collisions. So then that way we can more proactively assess safety. And we have a research project that we're just going to be starting, is that where Caltrans is building a turbo roundabout. It's a different type of multi-lane roundabout that tries to limit some of the internal lane changes. And what we're trying to do there is that obviously they're just building it right now. So we want to see what happens to the conflicts compared to the compared to what's happening right now. So right now it's a four-legged intersection, and we have certain conflicts that we've video recorded that data. Now, once the turbo roundabout is built, we're going to video record that new turbo data from the turbo roundabout, and we're going to use that the model that is being developed by Traffic Safe, which is the Transoft. The company is called the Transoft. Transoft has built a model to do the video analytics for us to be able to do the conflict analysis. So what we are hoping to see is that we can see the amount of reduction in conflicts that has happened since the turbo roundabout was instituted, and we can compare that to sort of what happens typically on a more traditional type of a roundabout. Okay, and then we can see how much safer the turbo roundabout might be. So there is a lot of applications of this, even though we are talking about it in the context of simulation. Nowadays, with the capabilities of video analytics expanding, there is a great way for us to sort of do that type of analysis more proactively, even in the real world. And all of that is based on these TTC and PET type measures that we derive from the video data. Okay, and then one more thing is that this video analytics could be also useful from one more perspective, is that you can actually take the video analytics of a certain real world location, and then you can compare the results that you're getting from that video analytics to the results that you're getting from vSIM. So you can even use that video analytics to validate your vSIM model even further, even at a more granular scale. Rather than just looking at travel times, now you can see, am I getting roughly the same number of conflicts that I'm getting in the video? Or am I able to capture similar numbers in vSIM? So there's a lot of applications. Those are just coming online. So I think this proactive assessment, I think, is going to catch on. I think collision data is just not, yes, we want to use that gold standard over time, but we cannot solely rely on that for safety assessment. So I think that practice has to change. It is changing. So I think you will probably see that adopted more and more as you all work, if you end up working in that area. So with that, I'm just going to stop here. And there's no ITE meeting today, right?
Oh, there is.
There is? Okay, so there is an ITE meeting, so attend that. Who's the guest speaker today?
Dr. Almas.
Okay, from the planning department. Yeah, that's going to be a great one too. So please go ahead and stop by at the ITE meeting today, and I will see you in the lab, if not sooner. And yeah, thank you very much.